Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is power distribution in series AC circuits. Our objective is to examine several illustrated examples of series AC circuits, including analysis of power. This lecture operates under the presumption the viewer has more than a passing familiarity with both series AC circuit analysis and AC power calculation, as illustrated in the AC circuit analysis playlist available at the Big Bad Tech channel. If you lack the requisite level of familiarity with these topics, please review the aforementioned supporting material and return to this lecture when you're so qualified. Mastery of power in series AC circuits necessitates active participation on your part, and as such, I'm encouraging you to please pause the lecture when asked to do so and attempt these example problems on your own. If your answers do not match those illustrated, by all means, feel free to rewind the lecture and correct any mistakes you may have made. Our first example problem features a series connection of two elements. The first element is a 240 ohm resistor, and the second element is a 22 microfarad capacitor. The source has an effective value of 120 volts and an excitation frequency of 60 Hz. Stage 1 of the example problem necessitates we solve for the voltage drop across each element, the current through each element, and the source current. Once we've got these values, we'll move on to stage 2 and examine power distribution within this series AC circuit. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should have obtained the following results. The complex impedance of the 240 ohm resistor is 240 ohms at an angle of 0. Let's call this impedance Z1. The complex impedance of the 22 microfarad capacitor at an excitation frequency of 60 Hz is approximately 120.6 ohms at an angle of negative 90 degrees. Let's call this impedance Z2. A Kirchhoff's voltage law analysis of this series circuit suggests that the rise E equals the summation of the drops V1 plus V2. Additionally, given that there is a single path for current in this series relationship, it can be stated that source current equals current through element 1, which equals current through element 2. If we solve for current through one element, we by extension also solve for current through the remaining element, as well as source current. There are several ways to obtain the desired voltage and current figures. Perhaps the easiest and most direct means of doing so is through the use of the voltage divider rule. The voltage divider rule suggests that V1 equals 107.2 volts at an angle of 26.7 degrees. Given we know the source voltage, and we now know the voltage drop across the first element, a rearrangement of the Kirchhoff's voltage law equation for this series circuit and solving for the unknown V2 suggests that V2 equals approximately 53.9 volts at an angle of negative 63.3 degrees. Note the summation of the individual voltage drops, accounting for direction, equal our applied voltage of 120 volts at an angle of 0 degrees. Ohm's law illustrates that the current through Z1 is 446.8 milliamperes at an angle of 26.7 degrees. An Ohm's law calculation for the second impedance yields the same result. Additionally, one can solve for total impedance where the summation of Z1 plus Z2 is 268.6 ohms at an angle of negative 26.7 degrees. Note the total impedance appears to be somewhat capacitive given the negative angle. Using this total impedance figure, Ohm's law also suggests source current will be 446.8 milliamperes at an angle of 26.7 degrees. This is a great way of checking your work. Note source current appears to be leading applied voltage by 26.7 degrees. This is to be expected given the somewhat capacitive nature of the total impedance. The phasor diagram of supply voltage and source current clearly illustrates this fact. The phasor diagrams for the individual elements illustrate some predictable properties. Despite employing an external absolute reference, it can be said that current through the resistor is perfectly in phase with the voltage across it. Similarly, it can be said that current through the capacitor leads voltage across it by a relative 90 degrees. Don't make relative phase shift hard. Look at the phasor diagram and ask yourself this simple question. Does current lead or lag voltage, and if so, by how much? Moving on to stage 2. Now that we've got reasonably accurate voltage and current figures for the individual elements and the larger circuit, see if you can calculate the apparent, real, and reactive power for each individual element and the larger circuit. Remember, there are numerous means of solving for power. However, they all employ only the relative phase shift between voltage and current. Given results of previous calculations include absolute references, this may necessitate active intervention on your part to format voltage and current as required. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's examine each individual element in turn and then take a look at the whole circuit. It can be said current through element 1 is in phase with the voltage across it, and there exists a relative phase shift of 0 degrees between voltage and current. Apparent power is the complex conjugate of voltage times current. Substituting our given values, we arrive at an apparent power figure of 47.9 volt amperes at an angle of 0 degrees. Resolving this into its real and reactive components demonstrates this resistor is directing 47.9 watts towards real power and no VARs towards a reactive interchange. This is to be anticipated given the entirely resistive nature of this particular element. Given there exists no relative phase shift between voltage and current, all apparent power will be directed towards real power. Alternate methods of calculating apparent power, specifically the complex conjugate of voltage squared divided by impedance, and the complex conjugate of current squared times impedance, verify this initial calculation. Let's now examine the second impedance. It can be said the current through the capacitor leads voltage across it by a relative 90 degrees. Apparent power is the complex conjugate of voltage times current. Substituting in our given values, we arrive at an apparent power figure of 24.1 volt amperes at an angle of negative 90 degrees. Resolving this into its real and reactive components demonstrates this capacitor is directing 0 watts towards real power and negative 24.1 VARs towards a reactive interchange. This is to be anticipated given the entirely reactive nature of a capacitor. Note the complex conjugate operation accounts for the negative reactive power sign and indicates current leads voltage. As can be expected, the capacitor directs all of apparent power towards a reactive power interchange. Alternate methods of calculating apparent power, specifically the complex conjugate of voltage squared divided by impedance, and the complex conjugate of current squared times impedance, verify this initial calculation. Let's now examine the larger circuit. It can be said source current leads the supply voltage by a relative 26.7 degrees. Apparent power is the complex conjugate of voltage times current. Substituting in our given values, we arrive at an apparent power figure of 53.6 volt amperes at an angle of negative 26.7 degrees. Resolving this into its real and reactive components demonstrates that the source is applying 47.9 watts and negative 24.1 VARs of reactive power. Is it merely a coincidence that real power for the whole circuit has the same value as that consumed by the single resistor, and the reactive power for this whole circuit has the same value as that supplied by the single capacitor? No, it is far from a coincidence and illustrative of a very important fact. Apparent power input equals apparent power output. This observation is merely an extension of our previous observations of power distribution in series DC circuits, only this time incorporating angles. Note apparent power can be considered as having both a magnitude and a direction. Accounting for angles, the apparent power delivered to the resistor is entirely pointed in the positive real horizontal x-axis, whereas apparent power delivered to the capacitor is pointed entirely in the negative imaginary vertical y-axis. Accounting for direction, the summation of the apparent power delivered to the resistor and the apparent power delivered to the capacitor yields a total apparent power figure of 53.6 volt amperes at an angle of negative 26.7 degrees. Importantly, this figure verifies our earlier calculation with respect to the source. Alternate methods of calculating total apparent power, specifically the complex conjugate of supply voltage squared divided by total impedance, and the complex conjugate of source current squared times total impedance, yield the same results. As we've observed, there are numerous methods of obtaining correct results and comparing them to predictable expectations. Let's try another illustrated example. Our second example problem features a series combination of 3 elements. The first element is a 180 ohm resistor. The second element is a non-ideal 560 millihenry inductor that happens to include a small internal resistance of 15 ohms. And finally, the third element is a 50 microfarad capacitor. The source voltage has an effective value of 90 volts and an excitation frequency of 50 Hz. Stage 1 of this illustrated example problem necessitates we solve for the voltage drop across each element and the current through each element and the source current. Once we've got these values, we'll move on to stage 2 and then examine power distribution within this series circuit. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should have obtained the following results. The complex impedance of the 180 ohm resistor is 180 ohms at an angle of 0 degrees. Let's call this impedance Z1. The second impedance takes a little bit more effort. The complex impedance of the internal resistance is 15 ohms at an angle of 0 degrees, whereas the complex impedance of the inductive portion of the second impedance at an excitation frequency of 50 Hz demonstrates that it has a value of 175.9 ohms at an angle of 90 degrees. These two elements are in series with each other internal to the second element. Therefore, Z2 has a value of 176.6 ohms at an angle of 85.1 degrees. It's still primarily inductive, however, the angle less than 90 degrees illustrates there is a resistive portion. Finally, the complex impedance of the 50 ohm capacitor at an excitation frequency of 50 Hz is approximately 63.7 ohms at an angle of negative 90 degrees. Let's call this impedance Z3. A Kirchhoff's voltage law analysis of this series circuit suggests that the rise E equals the summation of the voltage drops V1 plus V2 plus V3. Additionally, given there is but a single path for current in this series relationship, it can be stated that the source current equals the current through element 1, which equals the current through element 2, which equals the current through element 3. If we solve for current through any element, we by extension also solve for current through all other elements. There are several ways to obtain the desired figures. Again, perhaps the easiest and most direct means of doing so is through the use of the voltage divider rule. The voltage divider rule suggests that V1 equals 72.0 volts at an angle of negative 29.9 degrees. Ohm's law suggests that current through the first element is approximately 400 milliamperes at an angle of negative 29.9 degrees. The phasor diagram illustrates the current through the first element is perfectly in phase with the voltage across it. Given this is a series circuit, we can state that source current, current through element 2, and current through element 3 is also 400 milliamperes at an angle of negative 29.9 degrees. An Ohm's law manipulation demonstrates that the voltage across the second element is approximately 70.6 volts at an angle of 55.2 degrees. The phasor diagram illustrates that current through the second impedance appears to lag voltage across it by approximately 85.1 degrees. Finally, given we know the source voltage and have solved for the voltage across element 1 and the voltage across element 2, an algebraic rearrangement of the Kirchhoff's voltage law equation and solving for V3 demonstrates that V3 has a value of approximately 25.5 volts at an angle of negative 119.9 degrees. Despite the use of this external absolute reference, current through the third element appears to lead voltage across it by a perfect 90 degrees. Finally, the phasor diagram for the entire circuit illustrates source current appears to be lagging supply voltage by approximately 29.9 degrees. As a means of checking our work, an Ohm's law manipulation of source voltage and source current solving for impedance implies that our total impedance has a value of 225.0 ohms at an angle of 29.9 degrees. Summating the individual impedances Z1 plus Z2 plus Z3 yields this identical value. I've got a reasonable degree of confidence that these answers are correct, and we can now move on to stage 2 of our problem, solving for apparent, real, and reactive power for each individual element, as well as the larger circuit. Moving on to stage 2. Now that we've got reasonably accurate voltage and current figures for the individual elements and the larger circuit, see if you can calculate the apparent, real, and reactive power for each individual element and the whole circuit. Remember, there are numerous means of solving for power, however, they all employ only the relative phase shift between voltage and current. Given results of previous calculations include absolute references, this may necessitate active intervention on your part to format voltage and current as required. Don't make relative phase shift hard. Just look at the phasor diagram and ask yourself this simple question. Does current lead or lag voltage, and if so, by how much? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's examine each individual element in turn, and then take a look at the whole circuit. It can be said current through the first impedance is in phase with the voltage across it, and there exists a relative phase shift of 0 degrees between voltage and current. Apparent power is the complex conjugate of voltage times current. Substituting our given values, we arrive at an apparent power figure of approximately 28.8 volt amperes at an angle of 0 degrees. Resolving this into its real and reactive components demonstrates this first impedance is directing 28.8 watts towards real power and 0 VARs towards a reactive interchange. This is to be anticipated given the entirely resistive nature of this particular element. Given there exists no relative phase shift between voltage and current, all of apparent power will be directed towards real power. Let's now examine the second impedance. It can be said current through the non-ideal inductor lags voltage across it by approximately 85.1 degrees. Let's use one of the alternate methods to solve for apparent power. Apparent power is the complex conjugate of voltage squared divided by impedance. Substituting our given values, we arrive at an apparent power figure of 28.2 volt amperes at an angle of 85.1 degrees. Resolving this into its real and reactive components demonstrates this non-ideal inductor is directing 2.4 watts towards real power and 28.1 VARs towards a reactive interchange. This is to be anticipated given the largely inductive nature of this particular element. This non-ideal inductor is still dissipating a small but measurable amount of real power. Let's now examine the capacitor. It can be said current through the capacitor leads voltage across it by a relative 90 degrees. Let's use one of the alternate methods to solve for apparent power. Apparent power is a complex conjugate of current through the element squared times its impedance. Substituting our given values, we arrive at an apparent power figure of 10.2 volt amperes at an angle of negative 90 degrees. Resolving this into its real and reactive components demonstrates this capacitor is directing 0 watts towards reactive power and negative 10.2 VARs towards a reactive interchange. This is to be anticipated given the entirely reactive nature of this capacitor. Note the complex conjugate operation accounts for the negative reactive power sign and indicates current leads voltage for this particular impedance element. As can be expected, the capacitor directs all of its apparent power towards a reactive interchange. Now that we've got apparent power figures for each individual element, let's solve for total apparent power using an alternate method. Recall that apparent power in equals apparent power out. Summating the individual apparent powers S1 plus S2 plus S3 accounting for direction yields a total apparent power of 36 volt amperes at an angle of 29.9 degrees. Alternatively, one could summate individual dimensions of apparent power, where the total real power equals P1 plus P2 plus P3, and the total reactive power is Q1 plus Q2 plus Q3. Doing so yields a total real power of 31.2 watts and a total reactive power of positive 18 VARs. When the complex number in rectangular format 31.2 plus J18 is expressed as a complex number in polar format, you'll note it is 36 at an angle of 29.9 degrees. If adding up individual apparent powers accounting for direction and individual real and reactive powers seems too easy, we can always check this work with a quick calculation. Total apparent power is the complex conjugate of supply voltage times source current. Substituting in our given values, we arrive at a total apparent power figure of 36 volt amperes at an angle of 29.9 degrees. Resolving this into its real and reactive components demonstrates the source is applying 31.2 watts of real power and 18 VARs of reactive power. This confirms our earlier calculation. Apparent power in does indeed equal apparent power out. Let's try one last illustrated example problem. Our third and final illustrated example problem is somewhat different. It features a series combination of two elements, one of which is a resistor of an unknown magnitude, and the other an entirely unknown impedance. The source voltage is 240 volts at an angle of 0 degrees, with an excitation frequency of 60 Hz. Additionally, we're aware the effective magnitude of the voltage drop across the unknown resistor is 80 volts. However, we are entirely unaware of the phase shift with respect to the source. Finally, we're informed that the whole circuit is consuming 750 volt amperes of apparent power at a lagging power factor of 0.91. I'm asking you to solve for the complete phasor equivalent voltage drop across each element, the current through each element, the source current, and the apparent, real, and reactive power delivered to each element. This may take some thought and effort on your part since it's not a complete setup, as were the previous illustrated examples. By all means, pause the lecture and try this on your own. If you're struggling, here's a couple hints. Note the apparent power figure of 700 volt amps is magnitude only and does not include a direction. This being said, what does a lagging power factor of 0.91 mean, and how can you use this figure to your advantage? 2. Can you use the relationship of apparent power, voltage, and current to your advantage? 3. Finally, how does voltage relate to current for purely resistive, purely capacitive, and purely inductive elements? If you're tracking, you should have obtained the following results. First, a lagging power factor of 0.91 implies current through this series circuit lags applied voltage. Most likely, the unknown second element has some inductive characteristics. Numerically, power factor is several things, principally the cosine of the apparent power angle. Solving for the apparent power angle by taking the inverse cosine of 0.91, we arrive at an apparent power angle of roughly 24.5 degrees. Note the apparent power angle is assumed to be positive since we're clearly dealing with a circuit that exhibits inductive behavior and that the current is expected to lag voltage by a certain amount. Note the apparent power angle also implies that the total impedance of this larger series circuit will have an angle of 24.5 degrees, and source current should lag applied voltage by 24.5 degrees. These facts make excellent means of checking our work. Graphically, we can now illustrate apparent power for the whole circuit as a magnitude of 700 volt amperes pointed at an angle of positive 24.5 degrees. We can now resolve total apparent power into its real and reactive components. Total real power in units of watts is apparent power magnitude times the cosine of the apparent power angle. This is where power factor comes into play for individuals untrained in complex numbers. Power factor is essentially a pre-calculated stand-in for the cosine of the apparent power angle. Substituting in our given values, we arrive at a total real power figure of 637 watts. Total reactive power in unit of hours is apparent power magnitude times the sine of the apparent power angle. Substituting in our given values, we arrive at a total reactive power figure of 290.2 VARs. Note inductive reactive power, occasions in which current lags voltage, is assumed to be positive. Expressed using polar format, apparent power is 700 volt amps at an angle of 24.5 degrees. Alternatively, apparent power expressed in rectangular format is 637 watts plus J 290.2 VARs. Let's put these total apparent, real, and reactive power figures to the side and continue on with this problem. Now, given known apparent power and known source voltage figures, we can rearrange the apparent power formula to solve for source current, where source current equals the complex conjugate of total apparent power divided by source voltage. Substituting in our given values, we arrive at a source current figure of approximately 2.9 amps at an angle of negative 24.5 degrees. As we anticipated, source current lags source voltage by 24.5 degrees. Given this is a series circuit with a single path for current, it can be said the current through the unknown resistor 1 is also 2.9 amps at an angle of negative 24.5 degrees, as is the current through the unknown element 2. Current through series circuits is the same. Let's put this current figure to the side and take a look at a voltage distribution within this series circuit. A Kirchhoff's voltage law analysis of this series circuit suggests that the rise E equals the summation of the voltage drops, V1 plus V2. We know the voltage magnitude across our first impedance element is 80 volts. However, we don't know its phase shift with respect to source voltage. Or do we? Recall voltage across purely resistive elements is perfectly in phase with the current through it. Given source current has a phase angle of negative 24.5 degrees, voltage across the first impedance will also have a phase angle of negative 24.5 degrees. V1, represented as a phasor equivalent, would therefore be 80 volts at an angle of negative 24.5 degrees. We know the source voltage, and we now know the voltage drop across the first element. A rearrangement of the Kirchhoff's voltage law equation for this circuit and solving for the unknown voltage drop V2 suggests that V2 equals 170.5 at an angle of 11.2 degrees. We now know the voltage drop across each element and the current through it. Additionally, we know the total apparent, real, and reactive power for the larger series circuit. It's now simply a matter of calculating the apparent, real, and reactive power for the individual elements comprising this series relationship. Before doing so, let's pause to consider the phasor diagrams for the individual elements and how these may affect our power calculations. Additionally, let's calculate the complex impedance of these elements strictly for curiosity's sake. Despite employing an external absolute reference, it can be said that current through the element 1 is perfectly in phase with the voltage across it. This is entirely to be expected given its purely resistive nature. A manipulation of Ohm's law solving for impedance demonstrates that the first resistor has an impedance value of roughly 27.4 ohms at an angle of 0 degrees. Unknown resistor 1 is undoubtedly a 27.4 ohm resistor. Similarly, current through unknown impedance 2 lags voltage across it by a relative 11.2 plus 24.5 or 35.7 degrees. It can be said current lags voltage by 35.7 degrees. Note, current isn't lagging by a pure 90 degrees, indicating this unknown impedance isn't wholly inductive in nature and most likely includes some resistive characteristics as well. Most likely, we're dealing with an inductor that includes a series resistance. A manipulation of Ohm's law demonstrates unknown element 2 has an impedance of roughly 58.4 ohms at an angle of 35.7 degrees. Resolving this complex impedance expressed using polar format into a complex impedance using rectangular format, unknown impedance element 2 has a value of roughly 47.4 plus J 34.1. Unknown impedance 2 is most likely composed of a series combination of a 47.4 ohm resistor and an inductor that happens to have an impedance of 34.1 ohms at the given excitation frequency. Given our source has an excitation frequency of 60 Hz, a manipulation of the inductive complex impedance formula solving for inductance demonstrates the inductor in question most likely has an inductance value of roughly 155 millihenries. Note, it's not absolutely necessary to solve for individual impedance values. However, they make a great way of checking your work. Given element 1 is entirely resistive, we should anticipate it to consume nothing but real power. Given element 2 is both resistive and reactive, we should anticipate it to consume both real and reactive power. Importantly, given we solved for total apparent real and reactive power earlier in this example problem, we should anticipate the sum of the individual apparent powers, accounting for direction, to equal this total apparent power value. Let's examine power for element 1. It can be said that current through element 1 is in phase with the voltage across it, and there exists a relative phase shift of 0 degrees between voltage and current. Apparent power is the complex conjugate of voltage times current. Substituting our given values, we arrive at an apparent power figure of 233.3 volt amperes at an angle of 0 degrees. Resolving this into its real and reactive components demonstrates this resistor is directing 233.3 watts towards real power and 0 vars towards a reactive interchange. This is to be anticipated given the entirely resistive nature of this particular element. Given there exists no relative phase shift between voltage and current, all of apparent power will be directed towards real power. Let's now look at element 2. One could perform the exact same style of apparent power calculation. However, let's go about this in a different, creative manner. Given apparent power in equals apparent power out, and the fact that we know total apparent power, and we just solve for apparent power delivered to element 1, we can rearrange this equation to solve for apparent power delivered to element 2. Substituting in our given values, we arrive at an apparent power figure of approximately 497.2 volt amperes at an angle of 35 degrees. Resolving this into its real and reactive components demonstrates the second impedance is directing 403.7 watts towards real power and 290.2 vars towards a reactive interchange. This is to be anticipated given the mixed resistive and reactive nature of this particular element. As previously, one can think of apparent power distribution within this larger circuit from the perspective of solely the real and reactive power dimensions. Given element 1 is consuming 233.3 watts of power, and element 2 is consuming 403.7 watts of power, the total circuit must supply 233.3 plus 403.7, or 637 watts of power. Additionally, given element 1 is consuming 0 VARs of reactive power, and element 2 is consuming 290.2 VARs of reactive power, the total reactive power is 0 plus 290.2 VARs, or 290.2 VARs. Expressed using rectangular format, total apparent power is 637 plus J 290.2, and when apparent power is expressed as a polar equivalent, it is 700 volt amperes at an angle 24.5 degrees as previously. Finally, since we arrived at the apparent power figure for element 2 using simple addition and subtraction, one can use any implementation of the apparent power formula to check our work. Apparent power to the second element is the complex conjugate of voltage times current. This calculation also yields an apparent power figure of 497.2 volt amperes at an angle of 35.7 degrees. I've got a reasonable degree of confidence we're correct. Feel free to slam your notebook on the floor and moonwalk out of the lab if you arrived at these same figures. If not, feel free to rewind and revisit any section you may have missed and correct any mistakes you may have made. One last note tangentially related to power before we close out this lecture. Let's assume our larger series circuit represents a source, an electrical load, and a means of transmitting electrical power to that electrical load. The 240 volt 60 Hz AC source is obviously our source. And let's assume Z2 is our electrical load, the intended destination of electrical power, and where actual work is being done. Impedance element 2 might be the winding of a motor that's actually doing some work, like lifting, lowering, grinding, crushing, or moving something. Motor windings are often modeled as a resistor in series with an inductor, hence my earlier choice of this impedance combination. Impedance element 1, however, is the means of distributing power from the source to the load in the form of a long transmission line with some measurable amount of resistance, in this case 27.4 ohms. My question to you is this: what is the efficiency of this arrangement? You might rush to the incorrect conclusion that the source is providing 700 volt amperes of power and the electrical load is consuming 497.2 volt amperes of power. But this is entirely the wrong way to think about efficiency. Recall, apparent power has real and reactive dimensions. Real power is that amount of power measured in units of watts actually put to work lifting, lowering, grinding, crushing, or moving something. Reactive power, measured in units of VARs in contrast, is that amount of power cyclically exchanged with the source. Reactive power, while an important property of magnetic loads like motors and transformer, doesn't actually get put to work. This is where it's helpful to think of power factor, electrical efficiency, and mechanical efficiency as subsequent hoops through which apparent power must jump to yield usable real power output, where power factor is the first hoop, electrical efficiency the second, and mechanical efficiency the third. This illustrated example really only dealt with electrical power, but let's say the motor in question is driving some gearbox that has some mechanical inefficiencies like friction or misalignment of the shaft. The source delivers 700 volt amperes of apparent power to this larger series circuit. At a power factor of 0.91, only 637 watts is real usable electrical power. Power factor essentially strips apparent power of the reactive power dimension. 637 watts of real electrical power is delivered to this larger series circuit, consisting of a rather poorly conductive transmission line and the actual electrical load. The rather poor transmission system wastes 233.3 watts as heat considered a loss to this system, meaning only 63.4% of real electrical power, or 403.7 watts, arrives at the electrical load, Z2. Let's say inefficiencies in the gearbox driven by the motor rob an additional 53.7 watts from this system, meaning of the incoming 403.7 watts of electrical power, only 350 watts results in actual intended mechanical work. This system would have a mechanical efficiency of roughly 86.7%. Taken in combination, 637 watts of real electrical power went into this system, and we're seeing only 350 watts of usable mechanical power come out. This larger system would therefore have an efficiency of 63.4% times 86.7%, or roughly 54.9%. Again, power factor is the first hoop through which apparent power must jump to yield usable electrical power. Efficiency is that measurement of real electrical power efficiently transmitted through the system. My last question to you is this. If you could fix one thing in the system to make it more efficient, what would it be? Let's assume the source and the electrical load are fixed entities. Given this condition, you really only got two choices. Either fix the efficiency of the electrical power distribution system, or fix the efficiency of the mechanical power distribution system. By all means, pause the lecture and think about this. If you're tracking, you should come up with the following conclusion. The weak link in this cascaded system is obviously the extremely inefficient electrical power delivery system. The poorly conductive transmission line basically robs the motor of 233.3 watts of real power it could be using to perform actual work. If there's any money to be spent improving this larger system, it needs to be investing in upgrading the electrical efficiency. As a challenge problem to the viewer, I'm asking you to calculate the total efficiency of this upgraded system. The source remains 240 volts at an angle of 0 degrees, and the electrical load remains an impedance of 58.4 ohms at an angle of 35.7 degrees, and the mechanical efficiency remains 86.7%. The only thing that's changed is that the upgraded electrical transmission system now has a dramatically reduced impedance of 5 ohms at an angle of 0 degrees. As an independent exercise, I invite you to calculate the voltage across and the current through each element, the apparent, real, and reactive power consumed by each element, the total apparent, real, and reactive power, and the electrical and total efficiency of this upgraded system. If you're up to the challenge, by all means, pause the lecture and try this on your own. If you're tracking, you should have come up with the following figures. Current drawn from the source will be approximately 3.8 amps at an angle of negative 33 degrees. The source will deliver 921.2 volt amperes of power at a 0.84 lagging power factor. Real power input to the system is 772.3 watts, and total apparent power is 502.1 VARs. Z1 will consume 73.7 volt amperes of apparent power, of which 73.7 watts is directed towards real power and 0 VARs towards a reactive interchange. Our electrical load will consume 860.4 volt amperes, of which 698.7 watts is directed towards real power and 501.2 VARs is directed towards a reactive interchange. 921.2 volt amperes of power enters the system, and a power factor of 0.84 removes reactive power from consideration. Real electrical power input to this system is 772.3 watts, of which 73.7 watts is considered a loss by Z1. 698.7 watts arrives at our electrical load Z2. Therefore, this upgraded system has an electrical efficiency of approximately 90.5%. This being said, mechanical efficiency is still 86.7%, and we would expect to lose approximately 92.9 watts due to mechanical inefficiencies. In the end, this upgraded system yields 605.8 watts of usable mechanical power. In totality, this upgraded system would now be approximately 78.4% efficient. Alright, that's about it for this set of illustrated example problems. In conclusion, this lecture examines several illustrated examples of power distribution within series AC circuits. Additionally, we quickly examine efficiency calculations for AC power as a bonus round. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.